In this video, I'm going to go through the answers for the Hardy-Weinberg equation packet. This is what you should do instead of class 22. So going through this packet again, Hardy-Weinberg, my hope for this section is that a majority of these concepts you have had exposure to in Bio 1000. And so hopefully it's a little bit of a review. So again, complete the packet, turn it in, and then watch this video and double check your answers. So Hardy-Weinberg equation. Here, we're using the Hardy-Weinberg equation, which is a tool biologists use to make predictions about a population and to show whether or not evolution is occurring in that population. And so in model 1, we have controlled mating. So question 1, how many mating pairs are illustrated here? We have 12 mating pairs. Describe the parents in each of the pairs in model 1. We have one parent that's heterozygous and one parent that is a homozygous recessive. And you can use two Punnett squares here to determine the possible genotypes from the offspring of pairs. So you cross little b, with a big B, little b, and you find that 50% of them are big B, little b, or that heterozygous, and the other 50% are little b, little b. And that's the same whether the homozygous recessive is the male or the female. Question 4, for each of the mating pairs has one offspring, predict how many of the first generation offspring will have the following genotype. So none will be big B, big B. 6 of those 12 will be big B, little b, and the other 6 will be little b, little b. So you can imagine you have 24 beetles in a tank, just like model 1. How likely is the pairing scenario in model 1 to take place during the natural course of things within the tank? Well, it's not going to happen that way. That is too organized. It's not very likely that you'll get exactly those pairs lined up if they're just all mixing together in a tank. So why is model 1 labeled selective mating? Because here you are purposely putting together a heterozygous beetle with a homozygous beetle. Other pairings that could occur if they were just mating naturally is you could get 2 heterozygous beetles coming together or 2 homozygous beetles coming together. If the population of beetles in model 1 mated naturally, would your prediction for the offspring still be valid? No. This, by the Punnett squares, is just based on that specific type of pairing. If you had another pairing, you'd have to have another ratio. So number 8, discuss in your group the limitations of Punnett square predictions when it comes to large populations. And your specific answer may vary, but Punnett squares really only give a predicted ratio for one specific pairing. They're really only good for selective mating. When you have a population, it's impossible to do, or it quickly becomes impossible to do, all of the possible Punnett squares for all of the possible combinations. Okay, model 2, population genetics. Compare the organisms in the population of model 1 with the organisms in the population in model 2. The populations are exactly the same in terms of number of males and females, heterozygous and homozygous recessive. Number 10, individually match up 12 mating pairs for model 2 that might occur. Now, it's whatever. This is whatever 12 you put together of male with a female, male with a female, male with a female. Lots of options. Okay. Compare them with other people in your group. You will probably have different answers from other people in your group. Okay. Number 12, how many total alleles are in the population in model 2? So if each organism has 2 alleles and there are 24 organisms, there are 48 total alleles shown in model 2. And you could do that with math, or if you really needed to, you would count up all of the bees in model 2. Don't do that. Just do math. Okay. We're going to get into some more math. Everyone take a deep breath. Number 13. What is the probability of an offspring from model 2 getting a dominant allele? So of the 48 alleles here, the 48 bees, only 12 of them are big Bs. Only 12 are big Bs. So 12 divided by 48 gives you 0.25 of the dominant allele. What about the recessive allele? We have 48 alleles. 12 of them are dominant. That means 36. 48 minus 12, 36. 36 of them are that recessive allele. 36 over 48 gives us 0.75. If P is used to represent the frequency of the dominant allele, and Q is used to represent the frequency of the recessive allele. P plus Q equals what? So 0.25 plus 0.75 is 1. The answer is 1. Use your knowledge of statistics to calculate the probability of an offspring from model 2 having each of the genotypes. So to calculate big B, we take the frequency of big B and we times it by itself. So we're going to do 0.25 times 0.25 and we get 0.0625. To get little b, we take 0.75 and we times it by itself. So 0.75 times 0.75 is 0.563-ish. I rounded. And then for big B, little b, we could do the probability of the big B is 0.25 coming from mom. The probability of the little b coming from dad is 0.75. Multiply those two together. We get 0.188. And we need to times that by 2. And the reason we need to times that by 2 is because we can either get the big B from mom or we can get it from dad. And so being big B, little b, is this going to be the same chance as being little b, big B, right? Coming from either mom or dad. So we multiply that number by 2 and we get 0.376 approximately. Now, when we add those three values together, 0.0625 plus 0.376 plus 0.563, we should get approximately 1. And that's because there are only 3 possible options here, and the sum of those are 100% chance, or 1.0. So using P and Q as variables, we can write out a formula. So we could say that the probability of having a genotype big B is P squared. The probability of having a genotype big B, little b is 2PQ. And the probability of having a genotype of little b is Q squared. And this is our full Hardy-Weinberg equation of P squared plus 2PQ plus Q squared is 1. So in order to use the Hardy-Weinberg equation, 5 things have to be true about the population. This is super important. The population has to be large. Mating has to be random. All genotypes have to be equally likely to reproduce, i.e. there's no selection happening. No organisms enter or leave, so there's no immigration or emigration, and no mutations are occurring. So we have to have a stable allele from generation to generation. And this allows us to use the Hardy-Weinberg equation. If the genotype in a population matches exactly what is predicted with that equation, we say that the population is at equilibrium, is at Hardy-Weinberg equilibrium. If, however, we do the math and then we count up what's actually in the population and there is a disconnect, that means the population is not at equilibrium, is instead evolving. So number 20, could the requirements for a population be in Hardy-Weinberg? Consider the requirements for a population to be at equilibrium. In the natural world, is this likely to happen? Highly unlikely. Highly unlikely, right? It is hard to find a population at exact equilibrium because mutations occur. Sometimes mating isn't random. Sometimes people leave, people come out, right? Very hard to find. So let's do some math. Number 21, sickle cell anemia is a genetic disease. It is recessive, but the individuals within the homozygous recessive group, little s, often die prematurely due to the disease. This affects approximately 9% of the population. So what is that telling us? That's telling us that the Q squared equals 0.09. Q squared equals 0.09, or 9%. In order to find out what Q is, we need a square root. And don't worry, on the exam, you can use a calculator. So we take the square root of Q squared, we get just Q. We take the square root of 0.09, and our calculator tells us that it's 0.3. So Q equals 0.3 for A. If Q is 0.3, then we can say 1 minus 0.3 will give us P, and so P becomes 0.7. Now the frequency of our homozygous dominant folks is going to be 0.7 squared. Again, we use a calculator. We don't do this in our head. We use a calculator and we get 0.49. Number D, the letter D. The frequency of the heterozygous individuals, that's 2PQ. So 2 times 0.7 times 0.3, and our calculator tells us that's 0.42. Based on this, is the African population at equilibrium? No, because the ones who are homozygous recessive are dying off, the frequency of alleles is not stable. Natural selection is taking place. Okay, number 22. Individuals with the heterozygous genotype, big S, little s, exhibit resistance to malaria. This is actually true. A serious disease spread by mosquitoes. A, how might this affect the frequency of the recessive allele in the population? Well, this might increase the frequency of the recessive allele because heterozygous individuals will have better fitness in the environment, while homozygous dominant alleles will be more susceptible to malaria and may die off. So how might this trait affect the values we calculated? It might actually be closer to equilibrium because resistance to malaria is going to increase the Q value and decrease the P value to kind of counteract the effects of people who are homozygous recessive dying off from sickle cell. Okay, number 23. Consider the beetles in model 2. Imagine a change occurred where the white beetles were easier to spot, and so we lost 6 white beetles. Now we need to predict the genotype frequencies in the population. So we start again by calculating P and Q by counting up those alleles, and we find that now P is 0.33 and Q is 0.66. And then we use our equation to figure out the values of P squared, 2PQ, and Q squared. And so P squared becomes 0.109, 2PQ is 0.4356, and Q squared is also 0.4356. So are those numbers the same? So in number 24, we look at the numbers we previously got, we compare them to the numbers we just got, and you can see that they're different. And so that means the population is evolving. Okay. So last little set of questions here, the extension questions. The ability to taste PTC is due to a single dominant allele, T. You sampled 215 individuals and determined 150 could not detect the bitter taste of PTC, and 6 could detect, and 65 could not. So we need to calculate the frequency of our alleles here. And so Q squared, we're going to take that 65 who could not, and we're going to divide that by the total number of individuals here, which is 215. And so that tells us that Q squared is going to be 0.3. And then we take the square root of both sides and we get Q equal to 0.55. Based on that, we can then calculate P, and P becomes 0.45. And from there, we can figure out the frequency of our alleles, right? 2PQ gives us 0.495 for the heterozygous individuals. Number 26. We have 60 flowering plants that were planted in a flower bed. The same sort of problem set, right? We're going through the flowering plants. In the original population, P comes out to 80 over 120, which is 0.66. And our Q is 40 over 120, which is 0.33. That gives us our predicted genotypes of 0.4356 for our P squared. 2PQ is also 0.4356, and Q squared becomes 0.1089. So, do we have a difference between our observed and our expected data? Yes. And so that tells us that the population is not at equilibrium. Now, question 26 asks you to do a chi-squared analysis. I'm not going to expect you to do a chi-squared analysis. I just want you to look at those numbers and say that they're different, and that's it. Okay. So that's going to be our Hardy-Weinberg packet, and there'll be one more video about phylogenetic trees.